waiting for a second here because I think Dustin's probably turning on the mic. Okay, very good. Hopefully the folks online can hear as well. I am very happy today to welcome friend and colleague, Dr. Erin Macdonald, in part because she's a great speaker, but in part because this is a 3 years in process invitation. She was scheduled to give the colloquium the week Goddard closed in 2020. And we've been waiting ever since.
Sorry. We all did one thing to cause it, right? That was mine.
So we finally found a time that worked and where she could come back and actually have an audience, both online and in person. So to introduce Dr. Macdonald, for people who don't know her, she has a PhD in astrophysics, as well as being known for advising all of the current Star Trek series. We'll talk more about that later, I'm sure. Hails from Fort Collins, Colorado. Did her undergraduate degrees at University of Colorado at Boulder, where she dual majored in physics with astrophysics, cum laude, and mathematics. She earned her PhD at 25 years old from the University of Glasgow in gravitational astrophysics. Her postdoctoral research with the Laser Interferometer Gravitational Wave Observatory, LIGO, scientific collaboration on gravitational waves from dead and colliding stars and black holes, contributed to the 2017 Nobel Prize in Physics, though she had left the collaboration before their discovery. Just missed out on it.
It's fine. It's fine.
Laid the groundwork for it, though. She has taught at the college level, worked with the Denver Museum of Nature and Science, written and narrated numerous popular science podcasts, including an Audible original series produced by the Great Courses on the Science of Sci-Fi, which reached the March 2020 Audible nonfiction top 10 bestseller list. And in October 2022, she published Star Trek, My First Book of Space, a baby in the STEAM universe. Call her. Dr. Erin has been the science advisor for the entire Star Trek franchise. She is an internationally sought after public speaker, educator, STEAM advocate, writer, and technical consultant who explains complex physics and astronomy ideas to varied audiences. She's also the founder and owner of Spacetime Productions, a film company dedicated to lifting and sharing marginalized talents and story. So please join me in welcoming Dr. Erin to talk today about warp drives to tachyons.
Thank you. It is a pleasure to be here, everyone. Thank you. As Ken said, this is a long time coming, but it's an honor for me. We were joking earlier that because I was a theoretician, I didn't get to see any of the cool stuff that you all have here, which is a lot of cool stuff. So it's been a great time. And yes, so the weird, varied career that I had has landed me in Los Angeles working as a science advisor in film and television. And I started working on Star Trek in season 3 of Star Trek Discovery and basically everything since then. So I work on all of the current shows. However, you don't have to be caught up with those. This is mostly going to be referencing some old Star Trek and some physics. And I know we have people from varied backgrounds. So if you're watching and you're like, oh, I know this is Astronomy 101, just be patient because not everyone might. But I'll try to breeze through those, given the location. Anything else? Oh yeah, I forgot to put in my bio, I'm a character in Star Trek now. That was the thing. Yeah, they added in Star Trek Prodigy, rest in peace, Lieutenant Commander Dr. Erin Macdonald at Starfleet Academy. So am I a Q? I don't know. We'll see. But anyway, so yeah, basically what we're gonna do is we're gonna go through all the different sort of technologies, science, all kind of physics oriented that we see in the Star Trek universe, and talk about how Star Trek uses it, what science is real, what's not, where we kind of make some concessions, and then we'll have time for questions. So without further ado, I'm going to get started. I have a little video that basically captures my love and all of you for,
That is a great story.
Quite amusing, Dr. Hawking.
You see, Sir Isaac, the joke depends on an understanding of the relativistic curvature of space-time. If two non-inertial reference frames are in relative motion...
Do not patronize me, sir. I invented physics.
So we're going to talk about space-time first, because this is actually really fundamental to a lot of the technologies that we see in Star Trek, and also is what I basically did my PhD in. So it's my specialty. But as the joke goes, we had Newtonian gravitational, the idea of gravity from Isaac Newton, and that was basically force equals ma, and we had the mgg over r squared and all that fun stuff. But in the sort of 1800s, as we were getting better observing planets and starting to understand kind of what was in the sky, there was something weird with Mercury's orbit in particular. Now, some of you might know this story, but this is my favorite fact in the whole world. So Mercury's orbit precesses. It essentially traces out a flower shape as it goes around the sun. And according to Newton's law of gravity, that couldn't happen on its own. Basically, you would have to have another planet within the orbit of Mercury to cause that to happen, to be that push and pull on there. And so they were like, well, Newtonian gravity has worked for as long as it has, so there might be a planet there that we just haven't discovered yet because our telescopes aren't good enough. And they called it Planet Vulcan. They did. And because we knew where it should be, as the telescope started improving, we were looking for Planet Vulcan, and it wasn't there, and they couldn't find it. So that was sort of what kickstarted this idea of like maybe Newtonian gravity works for 98% of stuff, but when we're getting on these large scales, it's starting to fall apart. So it's a good approximation, but it's not the true understanding of gravity in our universe. And mathematicians had been thinking about our universe as a four-dimensional fabric around the same time as well. Sort of in the mid-1800s, late 1800s was when they started looking at that. And they were thinking like, okay, in our universe, we go forward, back, left, right, up, down. So you have 3 spatial dimensions that you can control. And then we also move forward in time at 1 second per second. We just don't have any control over that. And that was started, being adopted by the community and looking at ways to play with it. And Einstein's contribution was to add mass to that fabric. So that was, you have your fabric, you put a bowling ball on it, right? And then you see how it reacts. And if any of you have played with gravity wells at science centers, you can kind of flick a marble and get it to precess around the center of that gravity well. So Einstein came up with this idea, applied Mercury's orbit to it, and it worked. And, since then, we've obviously seen a lot of the indirect effects of space-time and leading up to the 2016 detection of gravitational waves, which was the detection of space-time itself moving, which is awesome. If the bowling ball on a trampoline thing doesn't work for you because you're like, well, what's above the trampoline? Or like, what's under the trampoline? I do have a pretty cool image of like a 3-dimensional space-time. I like to describe it almost as like mattress springs. If you imagine you kind of stick your hand in and then squeeze them together and they stretch towards your hand, that's kind of how we can think about space-time bending due to mass in a higher dimension. If this is giving you a migraine, don't think about it. Bowling ball on the trampoline works great. And we're going to be referencing since then. So from there, like I said, they kind of applied Mercury's orbit. And then the next thought was like, well, okay, so if it does that, then light, which is massless and doesn't dip space-time, would curve on it as it travels. And so shortly after Einstein kind of theorized this, the scientists waited for a solar eclipse. I think one didn't work, and then they sent out 2 parties for the second one. And they were able to see that the positions of the stars changed behind the sun when the moon blocked it. So the moon blocked it, the light from the sun, you could see where the stars were or appeared to be, and they were in different positions when the mass of the sun isn't there. So that was kind of another good indirect detection of space-time. And now, of course, we do this all the time with gravitational lensing. We use to be able to measure masses and also image really far background galaxies as like, I literally just walked past a bunch of these pictures. So I might be repeating myself for a lot of people here. But we use it a lot, and it's going to come back in Star Trek. So, but first, we're going to go into the Star Trek world. And it's important to note that Star Trek takes place in our Milky Way galaxy, not a galaxy far, far away. So we follow our rules of our understanding of physics. This is Earth. They develop warp drive. The Vulcans make first contact. We develop Starfleet, join the Federation, all good times. But we want to sort of travel around, but we're traveling around our own galaxy. Now, it's also important to note, this is more for the Star Trek fans out there, that while Star Trek refers to the quadrants in our galaxy, that's not an astronomer thing. Mostly because it's really hard to image our own galaxy because we have all that dust and gas and everything. So trying to image the gamma quadrant is super hard to do. And we try to travel around. So there was like the Dominion War, Deep Space Nine, going to the Gamma Quadrant. Voyager is literally being lost in the Delta Quadrant. So how do we travel around this galaxy? Because as we know, space is very, very big. There are big distances. Traveling at the speed of light is still going to make for a very boring 5-year mission. You're going to get to 1 star and then you're done. And so we come up with different ways to shortcut these great distances using science. And the first one is wormholes. So wormholes are a theoretical thing. You know, the first sort of paper that tried to establish what wormholes were, it was like 1970 something. And again, just using this idea that you can bend space-time, you can fold it, you can create a hole that punches through it. The analogy I like to use is, and I should clarify before I will say it again, we have not detected them. So they are a theoretical thing, which is my happy place. And imagine, you know, you take a roll of toilet paper and you crumple it all up and then you lay it all flat. Like our universe seems to be mostly flat, there still could be local bumps and ridges. And a wormhole could shortcut those. So you're not having to travel on the whole surface. You could just punch a hole through the folds and shortcut the distance from A to B. And so where we've seen this in Star Trek, Voyager, Eye of the Needle, early season 1 episode, high recommend. If you haven't watched it or you haven't watched in a long time, amazing episode. Voyager stuck in the Delta Quadrant. They're trying to figure out how to get home. They discover a micro wormhole that they name the Harry Kim wormhole. And they manage to communicate with a Romulan on the other side, and it's in the Alpha Quadrant. So they're like, this is a chance to go home. But the Romulan's being like super Romulan-y, and makes it very difficult for them. They beam him over, weird things are happening with the transporter, and then they realize that not only was it connecting to the Alpha Quadrant, spoiler alert, still a great episode, it was actually connecting in time as well. And he had come from the past before Voyager had got lost. So following the temporal rules that Janeway happily throws out later in her career, he doesn't tell anyone that they got lost. And it's a great episode. But what I like the most about it is when we talk about wormholes and we see them in science fiction, we mostly see them utilized to shortcut distances. We have to remember they're shortcutting space-time. So you do have a time coordinate in there that could be a different one. So that one was really cool. And then TNG, The Price, and its sequel episode in another series many years later, False Prophets. This is where the Barzan wormhole, if anyone remembers that, where the Ferengi find it and they are like super Ferengi. And basically this wormhole is just like doing this and it's ending up in different places and they end up, it's like a tail. I think they compared in the episode to a dog's tail wagging, like one side is fixed and the other one flies around. And then like Voyager finds these Ferengi later who have definitely Ferengi'd the planet. It's a great episode. And then like there's a whole series based on a wormhole where the Bajoran wormhole is connecting to the Gamma Quadrant. The Dominion War happens and it's my favorite series. It's based on a wormhole. And then in some of the newer episodes, we did actually use wormholes. So this was in Star Trek Discovery in season 3. Season 2, before I joined. So don't, if you had problems with that, don't come at me. But they have the Red Angel suit that's essentially, she's traveling through time, creating wormholes to all these different points in time. And then it ends with opening this wormhole and Discovery brings all of this evil technology and destroys it and goes into the future. And that's where season 3 starts. So the whole premise of season 2 to season 3 of Discovery is that they travel through a wormhole into the future. And then in season 4, we had the dark matter anomaly, which was essentially a species that was living on the outer edge of the galaxy. Spoiled that a little bit, sorry. I should have given a spoiler warning. But they are searching for different molecules. and they're essentially dredging the ocean with an artificial wormhole. And then they're able to track the other side and see where they're coming from. So utilized wormholes a lot in Star Trek, and all kind of for different reasons, right? Now next, of course, we have to do the classic. It's warp drive, right? Everyone thinks faster than light travel, you think warp drive, and that is from Star Trek. Now the mathematics of warp drive essentially say that nothing on the surface of space-time can go faster than the speed of light. That's a rule, we're not breaking that. But nothing says that space-time itself can't go faster than the speed of light. So the concept of warp drive is that you build a bubble of space-time around your ship, and then that bubble pushes you faster than the speed of light. Your laws of physics stay the same. Your sort of space-time area that is interior to that warp bubble is totally fine. All the laws of physics are great, but the bubble around you is a warp bubble that's pushing you faster than light. And what's important about that as well is that you have this, you have a sort of limited speed. If you want to go even faster, you can build another bubble of warp around your first bubble and start exponentially increasing your speed. And what's cool is we have these rules, right? I showed this earlier, but like when Voyager got lost 75,000 light years away, about 75,000, this is from an old video game. I just really like the image. But it was going to take time for them to get home. They didn't just say, all right, let's go to warp factor 8,000 and we'll just be home in a day. They created these rules. So, however, if you ask me how fast is warp factor 1, how fast is warp factor 2, people have tried. The rules, the way I see it is like it depends on your ship. It depends on the technology. So warp factor 1 on our itty bitty Voyager is going to be different than our massive galaxy class Enterprise D. But this concept of exponentially increasing your speed, bubble after bubble, until you end up wrapping all of space and time around your ship, and we get terrible episodes where people evolve into lizards, and it's great. But what's cool about warp drive is that the math does check out. Some of you may have heard of this, but people have been trying to figure out, I tried to figure out if I could calculate warp drive when I was procrastinating writing my dissertation, but you can actually start to apply some mathematics to it, where you condense the front, extend the back, sort of try to compensate for all of the distortions you're making. The issue is not, can space-time do this? The issue is how much energy it requires to do this. Now, we all know that E equals mc squared. We've heard that, right? Mass has energy. If you want to bend space-time, you need that bowling ball. If you don't have that bowling ball, you could use an equivalent amount of mass. But the amount of mass that encompasses just even a bowling ball is multiple nuclear bombs worth of energy. And the first time they tried calculating how much energy it would take to build this drive, one of the most popular ones is called the Alcubierre drive. So they tried to actually figure out how much energy it would take to build it, and they crunched all the numbers, and the answer they got was all of the energy ever has ever existed, will ever exist, beyond our comprehension. Not great. People have continued working on it, and the last I saw, which this is a couple years old, so I don't know if anyone else has done anything, but I saw that it was about the energy equivalent of a semi-truck. It's like as good as they got it. So again, that's still an insane amount of energy, and we have no idea how to capture that, utilize that, even how to start playing with space-time. But we're getting one step closer. And with gravitational waves, you can think about this idea that first we theorized space-time, then we saw the indirect effects of it in the gravitational lensing and Mercury's orbit and all that. Then we directly detected space-time based on gravitational waves. The next step is to learn to play with space-time, and that will be warp drive. So I remain optimistic. I don't know if the year 2063 is going to be there, but there was a whole World War III in between there, so who knows? Necessity, invention, necessity, all that fun stuff. Anyway, when they did start publishing the idea that warp drive could be a thing, of course, people who work in government were like, yeah, we're going to do this. And they made it look a nice little saucer shape on the front and also labeled it the IXS, Enterprise. So the Enterprise will live on. But now I've talked about gravity wells, right? Gravity wells, that bowling ball and the trampoline, they're all very different depending on what mass you have, and you can do lots of fun stuff with it. My favorite fact about gravity wells is that GPS satellites are actually the only practical application of our knowledge of space-time because they are far enough in orbit. I use GPS satellites. Other satellites that are at geo and further orbits all do this, but they're further out of our gravity well, so the time they experience is actually different than ours. On the surface of Earth, our time is going at a certain rate. We feel it at 1 second per second, but GPS satellites are actually going slightly faster. We're in the gravity well, so we're being dragged down. That's how I kind of try to remember it. But the further you get out of a gravity well, the sort of faster time is experienced. And this is going to come into play. But first, we're going to talk about where we've seen gravity wells in Star Trek. This episode is brilliant. Has a Dyson sphere in it. Scotty comes back. This is TNG Relics, where they discover a shuttle that had crashed because it had fallen into the gravity well of a Dyson sphere and wasn't able to escape. Scotty hid in the transporter, and then he comes back and goes on the Enterprise D, and then I cry, and it's such a good episode. So good. And then Voyager, Blink of an Eye, is another great episode. So this is where Voyager discovers a planet, and it looks weird, and I'm going to come back to it. They discover a planet where, as they're in orbit, they watch an entire civilization evolve over the course of like minutes or so. The people on the surface of the planet are experiencing time much faster than Voyager is. And then we had Tomorrow's Yesterday, classic TOS, and the one with the whales, where they slingshot around the sun to go back in time. In Tomorrow's Yesterday, they do this like it's an everyday routine. I don't know if you remember that. They were like, we have a job to go back in time to Earth. We're going to go, and no one questioned it, and it's totally fine. Voyage Home, they play with it a little bit more. But what I like the most about this is the utilization of gravitational slingshotting, which we do see and use as we explore our own solar system. This is a really cool chart. I wrote the name there because everyone asks. You can buy this. I have it. It's in my house. But it basically shows the path that every single thing we've sent into the solar system has taken. And you can see all the loops around different planets. What they're doing is they're utilizing a gravitational slingshot, which is essentially a way to adjust your velocity and adjust your velocity, your direction, your speed. Your momentum is what you're doing. You're creating a sort of collision where momentum transfers between the spacecraft and the planet. You're slingshotting around, but because of the mass differential between the planet and your little spacecraft, that gets a huge change in velocity, and the planet doesn't change its velocity hardly at all because the masses are so different. So that's, I love it. It's cool. All right, so that's gravity wells. They get trapped in them. They slingshot around them. Oh, how the gravitational slingshot to go back in time works is the way I've thought about it. As you're falling into the sun, right, into the gravity well of the sun, you increase your warp factor, which you start to build space-time around your ship while time is also being distorted in one direction, and then you magically go back in time. And I also could not tell you how you go forward in time to exactly where you were using that method, but it makes for great storytelling. Okay, next one, dilithium. So dilithium is this fictional material that's been around since the original series. It is a common misconception, and Scotty will give you this face if you think it, I'm a little friendlier, that dilithium is the fuel for a warp drive. It's actually not. It's essentially the regulator of matter-antimatter collisions in the warp core. So a warp core in Star Trek, at least the Starfleet ones, work where you put in deuterium and anti-deuterium into an intermix chamber, and then they collide and they turn into energy. And this is a thing. This is a science thing. We have done this. We have created this where you can take matter and antimatter. When they meet, they annihilate themselves and turn into energy. And in Star Trek land, that's how they get the energy to power the warp drive. But what the dilithium does is essentially acts like control rods in a nuclear power plant. So however the dilithium is sort of structured, which I have many thoughts on, I'll get to in a second, what it does is it's able to regulate the collisions that are happening. And then when dilithium breaks or you run out of it, then if the warp core is active, then it will essentially go critical. You get those feedback loops, and then the entire thing explodes, which is what we saw in season 3 of Star Trek Discovery. Now, this is where they went to the future, and they discovered that there's like no more warp drive, essentially, because of this thing that happened called the burn. And the burn, there was a signal that went out, and it essentially utilized resonance and fractured all the active dilithium for starships that were at warp. And it all broke, and they couldn't go to warp anymore. And that was the first gig I got, was to say, can you science that, please? I said, oh, God. Okay. So especially because dilithium has been around forever. So the first thing I did was say, is it dilithium? Is it one thing? Or is it a magical dilithium, which chemistry says can't happen? So we just established it's dilithium. It's its own thing. And then I fell down a really, really deep, dark rabbit hole, trying to think about what makes up dilithium. And so I thought, in the future, at some point, we discover what makes up dark matter. And what we discover about dark matter is there are these things that are like subspace gauge bosons. So subspace is that area above and below the trampoline. This is where the laws of physics and speed and everything aren't real. They work great in Star Trek. We use them all the time. The communication happens because of subspace buoys that pierce space-time, and so you can communicate faster than the speed of light. And I thought, well, what if there are gauge bosons or other fundamental particles that can exist there? And what if they exist in subspace and their presence bends space-time? And that's where dark matter is. It was a weird rabbit hole I fell down, but it was a fun weekend. And I was like, well, what if dilithium has both these particles and normal, tangible particles that we can actually see? And I called them complex gauge bosons, as in they exist in real space. And the way I think of subspace is almost like the imaginary plane in mathematics, and so the complex plane combines the both of them. That, we don't even have to get into that. But that was sort of what we thought of with the dilithium, because the rule I was given for the story of the burn was that it had to originate from a single point, and the signal had to travel faster than the speed of light, but it still had to propagate. It wasn't just instantaneous. So that's where all the subspace stuff started coming from. And because I went down that weird rabbit hole of thinking about dark matter and what the origins of it could be, we were able to actually name the nebula in which they find the origin of the burn. The nebula has a ton of dark matter, and we got to call it the Verubin Nebula after Vera Rubin. So that was very exciting for me. If you do want to go down the weird rabbit hole that I summarized for you, myself and Professor Mohammed Noor of Duke University, he did all of the biology of the burn because it, well, I won't spoil it for you. You can find out. But we wrote an article for StarTrek.com on the science, like a science article. So it's pretty fun. It's got more detail in there. But we're going to move on to transporters, one of our favorite technologies in Star Trek that we all wish we had. We've seen transporters the whole time. And of course, in the pre-Cochrane, i.e. our real science era, and the choices we make based on necessity of production, transporters were invented because it was too expensive to film shuttlecraft taking off and landing. So they came up with this idea of transporters, and then we built the science around it. But because of that, I use these 2 episodes as examples of how the transporter could work, because there's slightly different explanations based on the stories that we get out of it. So in Enterprise, Hoshi is like, not going in the transporter, death machine. She's not wrong. I'm with her on that one. But she basically thinks that it's going to break down all of your fundamental particles to tiniest bits possible, move them, and rebuild you on the other side. That's how that episode describes how the transporter works, is that it moves the particles itself. Then we get two Rikers, which, when he's trying to beam away from the planet, there's interference in the atmosphere, and he essentially gets created twice. It's like he starts to beam up, the signal reflects back down, and then he gets built out of something else on the surface of the planet. That's the idea, that you break down the body, you recycle that material somewhere else, which is dark, but you've mapped in data, essentially, where all the particles are. You send that information somewhere else, and they rebuild the body, the person, out of other material. Don't think about it too much. But that would be the explanation for second chances. That's how they describe it there. So there's never really been like a definitive way. The closest we got was in Star Trek Prodigy, when they discover the transporter for the first time. They say all of the matter is broken down into energy and then transferred somewhere else. So whether that's a data packet or whether that's how they're just describing breaking down all the particles, can be left up to interpretation. But as you all probably know, unfortunately, physics says transporters can't exist. And that is because of the only equation I have in this talk, Heisenberg's uncertainty principle. That it says the closer you get to looking at where an object is, the less information about its speed or its momentum that you have. The more you know about its speed, the less you know about its position. Favorite joke of all time is that a cop pulls over Heisenberg and says, "Sir, do you know how fast you were going?" He said, "Nope, but I know exactly where I am." And he said, "Well, you're actually going 70 miles an hour." He goes, "God, now I'm lost." Brilliant, brilliant Heisenberg joke. But so this means, if we want to transport something, whether it's the particles themselves or whether that's information, you want to know exactly where every single particle goes. And because of this physics principle, we can never know that. But Star Trek solved this problem by having a Heisenberg compensator. Yeah. They say it offhand. How does the Heisenberg compensator work? It works very well. Thank you for asking. This is my favorite example of science in any science fiction, because this is something that is just directly saying, we know we're breaking the laws of physics with this. We figured it out in the future. You don't need to know the details, but trust me, we know what we're doing here. Now, we've seen in the news, I'm not going to harbor on this too much, but we've seen in the news people are talking about like transporting particles, places that people are doing experiments. It's really more quantum entanglement experiments than actually moving particles from one place to another. But that's up for debate. I just want to clear that up because people always ask, like, well, people are doing experiments with transporters now, and it's more quantum entanglement experiments. It's just talking about transporting data instantaneously. So it all gets muddled up in the headlines and on the clickbait. We all know how it goes. Photon torpedoes. Oh, love it, love it. Photon torpedoes. Another great example of Star Trek technology. How do they work? If you think about it for half a second, you're like, wait, what is a photon torpedo? Because it's photons. Photons are particles of light. And when Nog is freaking out and goes, "Fire photon torpedoes," we see those torpedoes like move from the ship to another. It's not turning on like a laser beam. You actually see something tangible travel through space and then blow up or fly past whatever it was you're actually trying to hit. It's a little dark, but the way I think about photon torpedoes is they're essentially nukes, which is really horrible, but high energy photons, right? You're releasing like a ton of energy, right? And so that's kind of how I think of photon torpedoes, but again, it's a little weird to talk about. So next we're going to talk about cloaking devices, because you have to be able to see the thing you're going to fire the photon torpedoes at. Again, has been around since the original series, and people have tried to develop cloaking technology, invisibility cloaks, whatever. And to varying degrees of success. Some of it is like using the principle of chameleons that you take the information behind you and project it onto the front. Other examples are like bending light in a way such that you can't actually see a certain region. But that doesn't quite work for our purposes, because if you were going to do that to cloak something, then you go here and then you see it. So it doesn't work very well. But the main principle that you need for cloaking technology is you are essentially masking all of your signals. Now we know when we detect things in space, it's from emission or reflection. And so you don't want to be emitting any electromagnetic radiation, anything that could be picked up on the scanner when you put a cloak on. So you're masking not just your visible light, but your infrared light, your everything else. So don't keep it on too long, because you will cook yourself, which is fun. But we see it in, of course, The Balance of Terror. This was the first time we saw a cloaking device. This was when they encountered the Romulans. In Pegasus on Captain Picard Day, they're trying to find ways to detect cloaked Romulan ships. Of course, we had them, develop cloaking technology for Starfleet around the Dominion War with the Defiant and everything else like that. And then in this episode, such a weird, fun episode, but weird episode, this alien species cloaks themselves from detection on the ship. They're going around performing like sociological experiments on the crew, and they cloak themselves by constantly staying like in the future. Like they basically cloak themselves in time. So as soon as you try to see something, it's already moved, so it's not there. So they're like playing with how fast light emits, but then it would eventually hit your eyes. Again, that's another one where it's like, it's a cool idea. Don't think about it too much. But my favorite, I'm so jealous of this because it's the coolest thing. We had Heisenberg compensators. This is almost just, for me, this is cooler. They talk about in Star Trek Discovery, season 1, I think, they're trying to detect cloaked Klingon ships. And they are detecting no emissions, but they come up with the idea, well, it's not giving off any electromagnetic emissions, but it is massive. So what if we use gravitational lensing, microgravitational lensing, to detect a cloaked Klingon ship? The idea, because the Discovery can jump, that they basically image all of the stars in the background here, they jump here, image all the stars, image everything from all these different positions, then they can triangulate where the cloaked ships are. Freaking love this idea. And they do it like micro-gravitational lensing, because of course our resolution in the future is much, much better, and you're able to detect something on a small scale, not like the gravitational lensing we do now, but they use just classic triangulation in order to do that. They explain it super well, and that's how they detect cloaked ships. And it is like my favorite thing, gravitational lensing. And what's cool is, this is one of the ways that we detect dark matter, is like by using gravitational lensing to map out places where there's a lot of gravity, there's a lot of mass, but there's no electromagnetic radiation. So therefore, dark matter is not some weird, complex subspace particle. It's just Klingons, obviously, cloaked Klingon ships. Planetary scanning, I walked through like a million pictures that looked like this today, so I won't dwell on it too much, but they scan planets. They tend to, when they arrive to a planet in low Earth orbit, they do planetary scans on them, because science rules. Tricorders, another type of technology that we're like super close. We talk about different types of technology that we'll see in our lifetime, that we see in Star Trek. I would say tricorders are pretty much up there. And what's cool is definitely the wrong word. What's interesting about that is, like, especially the last few years, doing remote healthcare from a distance has become very important. So there's been a big drive to try to improve our methods of detecting both, health symptoms as well as diagnosis. And, even the fact like I'm wearing one of these is measuring my heart rate. It definitely thinks I'm exercising right now because I'm doing this. But, it's not, I'm not injecting it in, and it just has an uncomfortable amount of data on my life, I'll put it that way. And then probably almost a decade now, the Qualcomm put out a tricorder X Prize for anyone who could, what was it? It was like 13 physical, temperature, heart rate, blood pressure, all of those, as well as diagnose 7 diseases all remotely using a scanner. And someone won that. Like, the technology exists, but of course it's like the size of a room, and it's not quite, been developed to that point yet. And then we have inertial dampeners. Super easy. They dampen inertia. It's their seatbelts. But we do see them malfunction all the time. The way I have conceptualized inertial dampeners is basically, imagine you have the inner hull of a starship, and then you have the outer hull, and there's a gap there, and whatever you want it to be, maybe some sort of reversed non-Newtonian fluid that can absorb shocks. It can absorb like slower turns, but maybe, when you get shocked quickly, it's not as good at doing that. Those are the inertial dampeners. So I always like those. Last couple of things that I've got, and then we'll take some questions. Solar sails, another great episode. This is Deep Space Nine explorers. They basically discovered the Bajorans had a pre-warp method of traveling through space using solar sails. This idea that you could unfurl sails and use the momentum and radiation from the sun to hit the sail and accelerate you forward. And then because you're in space, you continue at that speed. You get more, and then by the time you're far away from the sun that you're not getting that many particles hitting it, you're going a pretty decent speed. And then in this episode, it's like they ran into like a tachyon buoy, which I'm about to get to tachyons, and it flung them to a different part of the local galaxy. And I'm sure a lot of you are aware, but this is a practical thing that has been looked at for a long time. Almost the reason for the Planetary Society from Carl Sagan was to try to develop one of these. And then 2017, I think, LightSail 2 successfully transferred orbits using only solar radiation. So they were able to prove that this method can be done.
Out an active tachyon beam to the other blockading ships. Now, in theory, any cloaked vessel that attempts to pass between our ships must cross that beam and be detected.
See, you're already thinking we've done cloaked ships. Now we got tachyons. All right, so tachyons I love, because they're like this idea that any normal mass dips down space-time. Tachyons invert space-time. And they're not real, because we've never detected them, but they are a conceptual physics phenomenon that like people do work on. And trying to figure out if they exist, could they exist, what would they come from? But the issue is that they always go faster than the speed of light. I'll come back to that in a second. But that's why it's like so hard to try to detect tachyons, because the causality is all screwed up. But I'm going to come back to this episode because we talk about the gravity well of a normal planet where it dips down space-time. In that gravity well, time goes slower than being outside of that gravity well. With a negative mass, with the tachyons, it's going to invert that. So if you're closer to the source of the gravity well where it's tachyons, your time is going to be faster than outside that gravity well, which is what they saw in blink of an eye. And they say it has a tachyon core. So we're good with it, sort of. Don't think about how they stay on the surface. But the most important thing with tachyons, and where we see them in Star Trek the most, have to do with causality. This idea that if you have an event A, and then some time later, this is space, this is time, events C and B happen, could A have caused either one of those? We have this light cone, so that's how fast the speed of light goes. And if event B is within that light cone, that means the information could have propagated slower than the speed of light, and so A could have caused B. You can think about it like dominoes, right? If I were to line up a whole bunch of dominoes, cover the whole thing, you see me tap one end. At some point later, the one on the end falls out. We didn't see or hear any of them fall. That would be like B. You'd be like, okay, that's pretty reasonable. In the situation with event C, that would be me going to tap the dominoes, and then the last one immediately falls out. And you're like, oh, that was not enough time for that information to travel, so it probably didn't happen. And that's how we think of causality. But the problem is that tachyons always live outside of that light cone. That's where they live. So anytime that there's causality issues, there be tachyons, which is what we see in TNG Redemption. This is that one that we saw a clip from, where they're trying to create a web of like warp drive, which of course is going faster than the speed of light, and then there will be an interim tachyon beam that can detect the cloaked ships. The tachyon eddy from Deep Space Nine Explorers flung them faster than the speed of light. When Janeway really violated the laws of temporal mechanics, she traveled through a wormhole to her past self to help them get back home earlier. When that wormhole that Admiral Janeway comes through, they see a huge emission of tachyons to try to detect it first. And then when they identify the temporal agent Daniels in Enterprise, they discover he's a time traveler because of an abundance of tachyons in his quarters. So usually when we see tachyons, we think time travel in Star Trek. And that's why, it's because of the causality thing. So with that, I have time to take a few questions. And also, you should check out my book, which is fun for all ages. Thank you. This was great. Appreciate it.
Thank you, Erin, so very much. We do have some questions online, but if people in the audience want to ask questions, please go up to the mics on either side. In the meantime, we'll start online. From Paul Whitehouse, kind of a statement, but maybe you have a comment on it.
Okay.
He says, with the description we hear these days of the extreme maneuverability of UAPs, presumably unidentified aerial phenomena, I can't help think of inertial dampeners.
Yeah, totally. I mean, am I cutting into the question? Is that the question?
Yeah.
Okay, all right, great. Yeah, I mean, absolutely, right? That we're seeing maybe objects, I'm a little bit skeptical, I got my Scully hat on, that are moving very rapidly in space. And that is that idea, is that our laws of physics and momentum and inertia can't really picture that there are aliens on those that are not getting like completely racked around. That's how I would phrase it. Yeah. No, I appreciate that though. It's a good question.
We'll take a question here. Jennifer.
Hi. Hi. Can you hear? Is this working?
It is now, I think.
I was wondering if you could comment on AI, artificial intelligence. It's, very hot topic right now. And yet with Mr. Data and the next generation, they were already exploring what that might mean if we develop intelligence that rivals or exceeds our own. How do they have a personal sense of self and conscience and time passage and meaning and all of that? So I just wondered if you could comment on artificial intelligence as it has been developed in Star Trek and how it's relevant to what people are very interested in about it today.
That's a great question. Here, I'll put this up so you can buy my book and you don't have to look at the Scotland. Not that that's not the worst thing. Yeah, I mean, what's interesting, and I really appreciate that question, especially because of the current world we live in. Most of the time now when we're seeing AI being talked about and advertised, it's really complex machine learning models, right? That you have multiple parameters, you have a huge data set that it's learning off of, and then spitting out like products. Now with true artificial intelligence, I think is that conversation of like data. And if you only ever watch one Star Trek episode in your life, make it Measure of a Man, especially these days, where Data goes on trial for his autonomy, if he has the ability to choose and based on his knowledge. And I think that, we've talked about the singularity in the past, right, where this idea that you train an AI model and then it becomes self-aware and starts learning by itself, that it, and there's been times where it feels like we're nearing that, but I think we're still so rooted in teaching these systems stuff that, first of all, it's not going to be very creative. As long as we don't show it Terminator, we can kind of avoid some of those disasters. We'll just keep showing it Star Trek episodes, but not have it write Star Trek episodes. That would be bad. But I do think that we're in a very interesting place with machine learning technology, not quite true artificial intelligence, if that makes sense. But I appreciate that. Thank you. One here and then we'll go there.
A comment from, I think one online and go back to you. A comment from me online. Thank you for the fantastic talk.
Thanks.
Where will the recording be posted? I guess that's a question
That's a
for me.
question for you.
If you go to the main Goddard Engineering Colloquium website, there's a menu item off on the left that goes to a page where videos are posted. I will warn everybody that be patient. We're having some trouble with the system that does that. It may be a while before you see it appear, but it will eventually be there.
And I do also have a YouTube page. I have not uploaded anything to it in a long time. I think it's called Dr. Erin Explains the Universe. And then there is also a playlist on there that shows like other appearances. And I just link to other YouTube where it's like where this would be,
Right.
So other talks that are similar to this. So if you want to see more, you can kind of go through there. And I get to have a cool interview with Jonathan Frakes on there. So just a little humble brag. Yeah.
Take another question from the audience here.
Hi, thank you for a really great talk. So I wanted to ask about, so in your role as a science advisor to Star Trek, what sort of creative input do you get to give? So say they come to you with something and you're like, okay, well, this wouldn't work, having your vast knowledge of the Star Trek universe. What kind of sort of creative input do you get to give back to them?
Yeah, thank you. That's a great question. So what's interesting is that working as a science advisor in Hollywood, it takes a really long time to get your foot in the door because a lot of writers that have had bad experiences with people who have been science advisors because they call up their cousin who works at NASA and they're like, hey, we're doing this. Does this make sense? They're like, no, that's dumb. Science doesn't work that way. And the way I approach it is the way I kind of advertise my science advising is that I do a yes and approach. Like you want to do some weird, wacky, multiverse time travel thing? Sure. Let's see what we can do and not explain stuff, which is most of what I do. Now, because of that, there's always a level of trust when there's a new show that's brought on. Now I'm starting to build a little bit more credibility, but even then when showrunners directly know they have me as a resource, that first season is usually just me getting scripts or outlines and giving notes back and just saying, rephrase this, don't explain this, does this make sense, and a little bit of dialogue. But then after that first season, then they start bringing me in earlier, and then we get to have more input. So I would say like the most input creatively that I've been able to give was on Discovery Season 4, where we did the DMA, like the whole development of that. We did a lot from the beginning, just first concept. Whereas like with the burn, they had already thought of the whole idea. They just wanted the science backbone added to it. And then too, what has been great and personally just a really special experience was working on Star Trek Prodigy. Because not only was I advising on the science aspect of it, have them explain transporters, let's have them explain how this works. I was also able to help develop the character of Rock Talk, who is a young girl who wants to be a scientist. So they were trying to like ask me about like, what was little Erin like when she wanted to like, how did she become a scientist? And so working on that was like really, really special to me because it was a little bit outside of that bandwidth of traditional science advising. Yeah, thanks.
Awesome, thank you.
Thank you. Good question. Another good question from colleague Carolyn Collins-Peterson. Whatever happened to the idea that overusing warp drive was somehow destroying or destabilizing the space lanes? This was posed in TNG.
Oh, it's such a good episode. It's like a whole just don't destroy the environment episode, which is still like it's hard to watch these days. Like, oh, we did. But the idea of that episode, I forget what it was called, but it was Next Generation. They discover like a region of space where warp travel is banned because space-time has been so rendered by it. And I love that idea where it's like you had a high traffic corridor where a lot of warp bubbles went through and it's like they stretched out a sweater. Like it just kind of rendered the fabric kind of unusable and they were at the risk of tearing it, that you weren't able to do it. So that analogy works really well for that episode and how they describe it. But we also have to remember, like, space is very, very big. and there is a lot of empty space. And as big and cool as these starships are, you're not, like, between, Earth and the next star system over, we're not running the risk of running the same path over and over and over again. You could have a crowded region of space. So we have some examples of overusing highway systems and warp drive, but the actual ability to do that would be rare, is how I would say that. Yeah, thank you though. Great question and great episode.
Unless, of course, you're trying to do the Kessel run in 12 parsecs.
Hey now. All right, we got one.
So I just want to make a comment about inertial dampers.
Ooh, please, yes.
So I always envisioned inertial dampeners as being implemented through artificial gravity.
Oh, yeah. Yeah, so the gravity generators are similar to the Heisenberg compensator in that they work very well. Right. But I do like that idea that we have, so for artificial gravity generators on the Enterprise, for example, you'll note that the Enterprise is not a 2001 Space Odyssey space station, right? It's not rotational artificial gravity. There's some electrical mechanics component to it. What I do love about that is that in the TNG technical manual, if any of you own that, I suspect there are a few, I have it as well, they talk about artificial gravity generators, and the schematic that they have includes, oh my God, I'm completely blanking on it. What's the thing where if you cool it, it's not semiconductors, that's the word that's stuck in my brain. You cool it down, then the electrical current goes faster? Superconductors, thank you. I was stuck on semiconductors. Superconductors. What was great is that I think that really ages when they wrote the technical manual, because that was at the time where those superconductors were like the rage of like, what's all the cool new technologies we can do with that? And the people who were doing the technical advising on Star Trek at the time were like, they make our gravity generators. I like that. That's cool.
Question from Herbert Matthews. What technologies do we have now that were only science fiction in early Star Trek? Examples might include compute voice recognition, augmented reality, and perhaps communicators.
Yeah, for sure communicators and that we're having video calls with people. I don't know if any of you remember that, but there is a scene where like Kirk, phones the medical bay and McCoy's face pops up on the screen, and now that's like he just Zoom called McCoy. He just FaceTimed McCoy. Like we're super used to that, but at the time that was unfathomable, and especially because it's on like a box CRT, old school, and the screen's that big and it's really poor webcam resolution. But yeah, those technologies, and I mentioned how we're kind of close with a tricorder. I would say another technology we're also close to that we might see some in our lifetime, and we already are touching it, is replicators. Now, I don't think we're to the point necessarily where we would say like, tea, coffee, black, coffee, black, tea, Earl Grey, hot. Woohoo! And it would just materialize in front of you. But I do think how much the 3D printing technology has improved over. Even 10 years ago, I would never imagine that I would own a resin 3D printer that's this big and sits on a table, and now like we have those and they're relatively accessible. In tandem with the knowledge that we are developing for synthetic food, the idea that now there was this huge, the Impossible Burger, Beyond Burgers, all of those hit the market and kind of flooded everything because they were able to synthesize the protein that makes red meat taste like red meat. And that was when all these companies started making these artificial burgers that weren't just like quinoa black bean patties that you just cried and imagined it was a burger. Like Beyond Meat is insane, like it's crazy, and Impossible Meat is just bonkers. And it's because of that synthetic food research. So you have these two technologies that are just massively increasing, and there's lots of efforts put toward them because of the necessity in our culture. And at some point, we're going to bring them together because Star Trek fans are also scientists and innovators and engineers. And we're going to say, I want a replicator. So we'll try to make it happen.
Going back to the gravity topic from Barbara S., is gravity plating possible in Enterprise? They captured a Gorn by increasing the gravity in the floor of the section where the Gorn was and he couldn't move. This should have been available in all future episodes where the crew is chasing someone in the ship.
I don't disagree. Thank you for that comment. But yeah, that was how the artificial gravity generators, however they work, they're unidirectional and are directly under the floor. So, and you imagine there is some plating. Now, okay, maybe, I will yes and this, why we haven't seen those is because they moved on from the Enterprise and it wasn't individual plates because maybe it was too expensive and too hard to calibrate and maintain, and they did entire floors at once, at which point chasing someone down a corridor, you're gonna get everyone. So that's my answer.
Quick thinking on your feet.
Thank you. I think we have time for one more, maybe? It's 4.
Okay, let's see what we got here.
There's many good ones. Thank you all, too. I appreciate the questions.
A lot of comments for you to read earlier. Any more questions from the audience here?
Last chance.
Okay, one last question here, and sorry for the ones that we're skipping. From James Aker, any comment on whether inertialess drive, E.E. Doc Smith and many subsequent authors, is superior to warp drive as a science fiction FTL workaround?
Not familiar with those.
Okay.
You got me. I mean, is that similar to, because there's like, they're faster than light travel and we see jump drives. Thank you for not asking about Spore Drive. I'm just going to leave it at that. I'm not going to talk about Spore Drive. But this idea that you could jump around, that's like you take space, you fold it, then you jump, and then you unfold it. And we saw that in Dark Matter series, in Battlestar Galactica. And then the other one that I'm trying to think of, it's not faster than light travel, but the Expanse, having a extremely efficient drive technology improve where they can accelerate at 9.8 meters per second squared, get halfway to your destination, flip, and that's how you get artificial gravity on the ship, as well as go really fast.
And maybe a fun ending comment from Loretta Nagel says, from some of your discussions here, there should be a script or a legend that says, "Here exist tachyons," instead of "Here abide dragons."
I like that. Thank you very much. And thank you all for coming to this. I'll be hovering around, I guess. And,
Yeah, we'll be down here for a few minutes afterwards.
Yeah, thank you. If you also have questions on the writer's strike, support the writers, support the actors. Unions rule. Yes.